So last time we wrote some nuclear decay equations, alpha, beta, neutron, proton emissions and captures, and we said atoms that are radioactive have very high mass numbers. And that is true, but it's a little more specifically, it's about the number of protons, the atomic number for the atom, versus the number of neutrons. And there's a certain ratio of neutrons to protons that allows an atom to be stable. And if you'll notice those dots on the graph, that's called the band of stability. Atoms that have those, or in that area, that proton to neutron ratio, are actually stable. Anything outside where those dots are is not stable. You'll notice the dark line on the graph, that's showing a 1-to-1 ratio between neutrons and protons. So the band of stability actually has a few more neutrons than protons, and that's considered stable. So where an atom is located with its proton to neutron ratio determines what kind of particle it will emit to get into the band of stability. So say I had an atom that's where that blue dot is, it's proton-neutron ratio. Now it could drop and lose a bunch of neutrons, or it could move to the right and gain a bunch of protons. But what normally happens more commonly is this sort of thing. So this atom, to get into the band of stability, would need to lose some neutrons, go down the x-axis, and it would also have to gain some protons, move to the right on the x-axis, and that would get it into the band of stability. And that usually is a beta decay, because if you remember that reaction, that special reaction that triggered a beta, an electron being produced, a neutron spontaneously decomposes into a proton and an electron, and that's the beta particle. So whenever you have a neutron to proton ratio that comes out in that region A, the atom will go through beta decay. That's its quickest way of getting into the band of stability. If an atom's neutron to proton ratio puts it in region B here, the easiest way to get into the band of stability would be to take this path. And that would be a decrease in the number of protons at the same time that neutrons are increasing. And that's the exact opposite of what we had for a beta particle. That's called an electron capture. Just like a satellite orbiting the Earth can lose power and its orbit decays and it ends up crashing through the atmosphere and burning up or hitting the Earth, an electron can do the same thing. Electrons in the first energy level, or the 1s orbital, can actually decay, lose energy, and end up crashing into the nucleus. And when it does that, if it hits a proton in its place, now you have a brand new neutron. This is the exact opposite reverse reaction of what we had for a beta particle. Any atom past that dotted red line needs to lose, move in sort of this path, and it needs to lose neutrons and also lose protons. And the only particle we had that was protons and neutrons was an alpha particle. An alpha particle is 2 protons and 2 neutrons, and so you would be losing both of those particles. So use the graph to answer those 4 questions on the bottom of page 21. If you look on page 22, there's a little activity about radioactive half-life. If I had this reaction happening, and at time 0, so say we're measuring time in seconds, at time 0, if I had 100 grams of uranium and 0 grams of thorium, and then the reaction started, alpha particles started being thrown off, forming some thorium, we would lose mass on the uranium side and gain mass on the thorium side. And the thing about nuclear reactions or chemical reactions also is that those 100 grams do not instantly become 100 grams of thorium. Reactions take time to go, and that's the concept about radioactive half-life. So to simulate the time it takes for one of these reactions to occur, we would have done this activity at the top of page 22. We would flip coins, shake coins, dump them on the lab table, and then take any that were heads out. Those would represent atoms that have gone from uranium, thrown off the alpha particles, and become an atom of thorium. The ones that were tails, we would leave, those are still uranium, and we would flip those and continue on, and we would find we would have less and less pennies left at the end of each round. So we would have combined all our data, and we would fill in our class totals like we have here, if you want to take a minute and write that in that right-hand column on page 22. And you notice that the number of uranium atoms left as time goes by decreases, which means we would have more thorium as the reaction went on, and then we would graph those. So go ahead and take a minute and graph the trial versus the number of coins. So we would get a graph that looks something like this. You notice that the amount of the uranium decreases over time as we go through each trial. So go ahead and answer the two questions on this activity. So in the penny example, one trial was the time it took for half of the pennies to go through the reaction. One more trial and half of those pennies went through the reaction, and that's called the half-life. Half-life is the time it takes for half the material to go through the reaction and become whatever element it's going to become on the other side of the equation. So in this case, on number 1 on page 23, the half-life for this reaction is 20 seconds. Every 20 seconds, half of whatever the uranium mass is will go through the reaction. The other half will just sit there as uranium, having done nothing. So the first thing we need to figure out is how many half-lives are going to go by in this reaction. We're going to take the total time of 80 seconds and divide by what the half-life, the T1 half period is in 20 seconds. And that would tell us that 4 half-lives are going to go by in this reaction. So 4 half-life periods will go by in that 80 seconds, 4 20-second periods. So to figure out how much is left of the uranium that has not reacted, which is what the question is asking, we would start with 100 grams. And if after 20 seconds, 50 grams would be remaining as uranium. The other 50 grams went through the reaction and produced thorium. Another 20 seconds, half of that 50 grams is going to be sitting there as uranium. The rest went through the reaction. So now we would have 75 grams of thorium, the 25 grams of uranium that has not reacted. And we need to go 2 half-lives, so another 20 seconds. There would be 12.5 grams left as uranium. And after the last 20 seconds of our 80 seconds, we would cut that mass in half again, and we would have 6.25 grams of uranium. So the question asks, after 80 seconds, or 4 of those 20-second half-lives, how much remains as uranium? It would be 6.25 grams. If they ever asked the amount of thorium, it would be 100, our total mass, minus 6.25 is the mass that you would have of that product, the thorium. So question 2 has platinum-195 throwing off a proton and becoming iridium-194. And this has a much longer half-life, which means that the platinum-195 is much more stable. It takes a much longer time for half of the material to go through the reaction. So it reacts, it's a slower reaction rate. And so the first thing we need to do is figure out how many half-lives have gone by. And so the time we're going to run this reaction or track this reaction is 48,220 years. And we're going to run the reaction for, theoretically, 24,110 years. And so 2 half-lives will go by. So the mass of the platinum will cut in half 2 times. So you can say 100 grams that we're starting with, divide by 2, divide by 2. That would be how much mass is left after 2 half-lives, or you can show it like this if you want to. After 24,110 years, we would have 50 grams remaining as platinum, and the other 50 grams would now have become thrown off the proton and become iridium. And then after another 24,110 years, we would have 25 grams left as the original platinum-195 that has not reacted. The other 75 grams did react and go through the reaction and form iridium. So the answer to the question would be 25 grams. So you can work the rest of the problems on page 23.